Hello everyone, I'm Chancellor Gary May. I'm so glad you could join us for our first plugged-in event of the fall. Today you have a front row seat. You're going to see how UC Davis physicians, scientists, and engineers are developing tools and methods that will help us better understand the brain and how to treat neurological disorders. As one of the few universities with world-renowned programs in neuroscience, engineering, and human and veterinary medicine, UC Davis is at the forefront of innovation and discovery. Neurological disorders are a pressing concern. In 2017, more than 200 million Americans, that's 60% of the population, were afflicted by at least one neurological disorder. Scientists and engineers at the UC Davis Center for Neuroengineering Medicine are working to repair, restore, and augment human capacity to benefit society. Advancements in electronics, machine learning, systems engineering, and neuroscience are leading to tremendous growth in the neurotech industry. So there's a growing need for cross-disciplinary collaborative education. UC Davis has a long history of working collaboratively across disciplines to tackle the world's most pressing challenges. It's through this culture of collaboration that we're able to empower the brightest minds, to ask bigger questions, explore greater possibilities, and push the boundaries of what's possible. Upon graduation, our students will embark upon professional journeys in academia and industry as researchers, educators, neuroengineers, physicians, as well as careers that don't even exist yet. During today's event, you'll hear from 4 faculty members. They've been building the foundation of the Center for Neuroengineering and Medicine at UC Davis, while at the same time sparking innovation and creativity in the leaders of tomorrow. I hope you find their insights as inspirational as I do.
Good afternoon, welcome and thank you for joining us today. I'm Andy Fell. I'm a News and Media Relations Specialist here at UC Davis, focusing on math and physical sciences, biological sciences and engineering. In my job, I'm privileged to get an insider's look at the fascinating research that goes on across campus and meet the people who do it. I'm delighted to serve as moderator for this plugged-in event. We hope these events provide you that insider's look at the exciting things happening at UC Davis. Today, our 4 speakers will talk about how the Center for Neuroengineering and Medicine is working to repair, restore, and augment human capacity of a common goal of providing benefit to society. After we've heard from our speakers, I'll open it up to a Q&A session. If you've already submitted questions, thank you. You can also submit questions throughout the event by using the Q&A feature at the bottom of your screen. If you have a question for a particular speaker, please be sure to mention their name in your question. Lastly, after the Q&A, we'll ask you to fill out a short poll. The poll will give us insight into topics that interest you and help us plan for future events. And now it's my pleasure to introduce Dr. Carolyn Patton. Dr. Patton is a neuroscientist and physical therapist. She directs the UC Davis Biomechanics, Rehabilitation, and Integrative Neuroscience Lab and is a co-director of the Center for Neuroengineering and Medicine. Dr. Patton specializes in assessment and treatment of motor dysfunction associated with adult and aging neuropathology, such as stroke. Her research focuses on understanding the neural basis of human movement, investigating human motor control, and learning from a perspective of neuromechanics. Please welcome Dr. Carolyn Patton.
Thank you, Andy. Today, I have the privilege of representing the Center for Neuroengineering and Medicine. On behalf of co-directors Dr. Karen Moxon in Biomedical Engineering and Professor Sanjay Joshi in Mechanical and Aerospace Engineering, welcome. Thank you for joining us this afternoon. As Andy indicated in his introduction, we're a newly formed center here at UC Davis. This might cause you to ask 2 questions. First, what is the center? But also, with so much research and academic activity, why do we need another center? The unique focus of the Center for Neuroengineering and Medicine is translation, clinical and scientific translation. The pipeline from discovery to delivery, from bench to bedside, is lengthy. It doesn't matter if it's a pharmaceutical agent, a device, a clinical procedure. Following discovery and fundamental research, the process requires multiple stages of clinical trials, regulatory approvals, and finally, implementation. In fact, the median time from concept to implementation is 30 years, often longer. And if you think of this from the perspective of a patient, this is literally a lifetime. The path along this route is fraught with challenges. periods where interest wanes, funding mechanisms gap, progress stalls, and many discoveries are ultimately abandoned. In our business, we often refer to this as the valley of death. And this leads to our vision for the Center for Neuroengineering and Medicine. We believe that by leveraging the strengths of UC Davis in engineering, across disciplines, in neuroscience, in medicine, and also bringing in contributions from humanities and law, these provide the legal and ethical foundations for today's technical challenges. We can create a synergy that would accelerate the translational timeline and diminish the impacts of the valley of death. We also see our center as an opportunity for intersection between disciplines, intersection between campuses, and intersections between collaborators, investors, and other research partners. And this brings us to the structure of our center, which is organized in 4 thematic research thrusts. The first of these is human performance and rehabilitation, followed by prosthetics and human-machine interfaces, cognitive neuroengineering, and finally, neuroscience and computational tools. Today, we'll have representatives from each of these 4 research thrusts to give you a brief overview of the activities that they are working on. Here I'll shift gears and talk about the first of our research thrusts, which is human performance and rehabilitation. Research in this thrust centers around the theme of movement and rehabilitation and restoration of human movement. If we think about how do we interact with the environment and some of the activities that make us most human, things like holding a paintbrush in your hand, playing a musical instrument, participating in a high-level athletic activity. These are very important pursuits for most of us and things that give us meaning in life. There are other activities as well, such as walking, feeding, dressing. These are the types of events that allow us to care for ourselves and provide us autonomy. In common, these activities involve the control and regulation of movement and also the integration of sensory information that helps us to understand how we are moving in 3D space. These functions are compromised in disease, especially in neurologic disease, stroke, spinal cord injury, MS, I could name many. And in the aggregate, our goal is to address this problem of neural control of movement with the goal of reducing the disabling consequences of neurologic disease. Here at UC Davis, Dr. Will Joyner is using movement as an assay of human brain health. He uses a fairly straightforward robotic paradigm. This looks very much like the figure in the top left here, where it looks very much like a video game where people are performing simple movements, grasping, reaching, pushing, and he alters the sensory information that they encounter. From this, he can take the data, as he models the data, he can determine how people integrate these different sources of information to form a central estimate of their movement or of the model of their body in space. He is currently working with this paradigm to probe working memory and the ability to categorize different forms of information in children with ADHD. And he's finding that movement can be used to quantify impulsivity and choice certainty. This same robotic paradigm can be used to evaluate human motor learning. So if we have people perform these simple tasks repeatedly, tens, hundreds, thousands of times, we can illustrate trajectories of learning. And there are different processes that are quite characteristic in healthy individuals. What he is finding is that people with Alzheimer's disease or Parkinson's disease have different trajectories of either learning or decay, as displayed in the right-hand panel, and that these mechanisms, which involve different pathways of the brain, are distinctly altered in these different disease states. So pulling this together, he is working towards using these types of movement tests to develop biomarkers of brain health, but also markers of disease progression. The thing that's very exciting about this is it's entirely non-invasive, and especially in the case of the children, but actually for children of all ages, it's very much like playing a video game and much less threatening than a medical procedure. A major line of research in my lab is looking at recovery of function in people who have had a stroke. So a major characteristic of people who've had a stroke is that their walking is very impaired. And what may be less recognized is that among these people, if they pursue rehabilitation to improve their walking, only about 50% of people who engage in rehabilitation actually improve or respond to that walking function. So this is for two reasons. One is that the neurobiological manifestations following stroke are highly varied. Some people are very mildly affected, some people are very, very severely affected. And the second reason is that the rehab interventions that are used these days are fairly uniform. And so there's a big mismatch in applying essentially a one-size-fits-all treatment paradigm to a vastly heterogeneous pathology. So work that we're doing here at UC Davis in combination with the Comprehensive Stroke Center is we're using transcranial magnetic stimulation to test the nervous system integrity that is retained following the stroke and evaluate that in conjunction with walking function, and then model that into a predictive biomarker. And our goal with this work is to determine categories of functional capacity for recovery and from which we could assign people to more specific treatment paradigms. To that end, new work that we have just initiated involves computational modeling of biomechanical data. Well, what do I mean by that? We can collect movement data from people walking. And what we're illustrating here, each of these red lines represents a muscle. This green line represents a force that a person produces when they're walking. We can collect data from a person today, regardless of how well they walk, how slowly they walk, how impaired they are. And my colleague BJ Fregley, with his computational approaches, is able to predict novel walking patterns, which we believe represents the best possible walking pattern that an individual with stroke could produce based on their residual physiology. We see developing these predictive models as a way to establish a roadmap, and these roadmaps could be used by rehab clinicians in order to identify procedures to help them get to that best possible movement outcome. A third approach is using targeted neuromodulation. And our vision in this project is by having people walk on a treadmill that gives us force information as they walk, we can provide the force signal as a very ready feedback mechanism in real time. And working with our colleagues who do adaptive machine learning, we are able to update this feedback on a subject-specific basis as they progress through a rehab program. In addition, we want to combine this approach with paired associative stimulation, which is a way of modulating brain activity, uses a combination of TMS and peripheral sensory stimulation. And we have found that we can target it specifically to the portion of the walking cycle where people are impaired and will benefit most from receiving the feedback in combination with the modulatory stimulation. So taken together, our approaches here in this research thrust provide us interactions among clinicians, scientists, and engineers to advance understanding of the fundamental neurobiology of impaired motor control and bring to bear advanced approaches that will advance recovery and restore motor function. Thank you for your attention. And with that, I'd like to pass this conversation back to Andy.
Thank you, Dr. Patton. I'd now like to introduce Dr. Jonathan Scofield. Dr. Scofield works to improve user acceptance and promote the seamless integration of humans and assistive medical devices, leveraging techniques in biorobotic control and feedback, sensory motor interfaces, and cognitive perceptual neuroscience. His research is at the interface of mechanical and electrical engineering, neuroscience, and rehabilitation medicine, addressing unmet clinical needs and understanding how humans engage with intelligent technologies such as robotic prostheses. Please welcome Dr. Jonathan Scofield.
Thank you, Andy. My name is John Scofield. I'm an assistant professor in mechanical and aerospace engineering, and today I'm going to be talking to you about some of the very exciting and very interdisciplinary work our center is performing in the areas of prosthetics and human-machine interfaces. Before I get into it, I wanted to prime us with a question, though, and that is, how do I know that I am me? Specifically, how do I know that my body belongs to me, and how do I know that the actions I perform with my body are my own actions? Simply put, there's no one answer to this question, but what we do know is that our brains are constantly making this distinction. And so whether I'm interacting with a smartphone or a semi-autonomous vehicle, I'm going to be acutely aware of where my body and my actions end, and where the contributions of the machine begin. This is important to recognize, because as humans, we tend to become frustrated with technology. We tend to blame technology for errors. And we do this to so much of a point that we will actually blame technology often for errors that we may have initiated in the first place. And so recognizing that our brains are telling us that we're separate from the machines we interact with, and that frustration and blame are constantly accompanying these distinctions, we can ask the question, what happens if we blur the lines between the machine, the human, and the cooperative action? This has important implications in numerous contexts, one of those being robotic prostheses. Robotic prostheses are interesting because replacing a lost limb with a mechanical appendage is really a solved problem from an engineering mechatronics perspective. But where the challenges lie is in the communication. Telling a robotic limb to perform an action and having that limb communicate what it's doing, how it's moving, how hard it might be grasping an object. The way we do these things are dramatically different than the way that we interact with our own physiological appendages. This breakdown in communication is a driving factor behind prosthetic abandonment, and right now we're seeing about 25 to 50% of clinically prescribed robotic prostheses are being left in people's closets. They're being abandoned. So at UC Davis, we're working to address this problem. We're working with surgeons at UC Davis Health who are performing nerve reconstruction surgeries. They're taking the nerves that used to service the now missing limb, they're turning them around, and they're plugging them in to the nerves and the muscles that remain after amputation. This is great for prevention of things like nerve-related pain and phantom limb pains, but at our center, we're actually leveraging this to allow for more intuitive control of robotic prosthetics. So if you ask an individual to think about closing their missing hand, whether that's in a pinching motion or a full fist, we can actually measure the muscular activity. We can then apply machine learning to recognize patterns in that muscle activity. And right now, with about 81 to 99% accuracy, we can actually pick out what that person is trying to do with their missing hand simply by measuring this rewired muscle activity. We can then link these predictions to the appropriate prosthetic movement, and we now have mind control over a robotic prosthesis. Interestingly, we can actually stimulate some of the skin in these rewired areas, and it can allow us to produce sensations of touch in the missing hand for these individuals. Strategic vibration of these rewired muscles can actually allow them to feel illusionary sensations of their missing hands opening and closing. And when you provide someone with a robotic limb that responds when you think about moving your missing hand, they feel their moving hand or their missing hand move, and they also feel touch to their missing hand. We've provided the brain with all of the pieces it needs to actually be tricked into believing that that robotic appendage is a part of the body. So we have mountains of evidence to suggest that individuals are actually beginning to embody their prosthetic limbs. And some of the more compelling evidence comes when participants change the way they speak about their robotic prostheses. They'll start often at the beginning of our sessions saying things like, "when I tell my prosthetic to close." And at the end of our testing sessions, they're often saying, "when I close my hand." These are small grammatical differences, but huge differences in the way that user is interacting with and perceiving their prosthetic limb. Finally, at UC Davis, there is a depth of knowledge in a number of complementary areas in which this prosthetics work has built the foundations to allow us to explore unique applications. For example, we're working with the Shriners Hospital and children who are born with limb deficiencies to allow them to operate dexterous robotic prostheses. We're working with NASA to allow astronauts to rapidly learn to operate externally mounted spacecraft robotics as an extension of their own bodies. And finally, we're working with supernumerary robotics, additional robotic appendages, finding ways to intuitively control these devices with the intention of extending the capabilities of the human body beyond the limitations of a two-legged, two-armed body. So at UC Davis, there's a number of unique applications and unique areas in which we can apply our work in human-machine interactions. Thank you.
Thank you, Dr. Scofield. Now it's my pleasure to introduce our next speaker, Dr. John Dietrich, Professor of Neurobiology, Physiology and Behavior in the College of Biological Sciences. His lab's primary research is on neural mechanisms underlying higher order brain functions that link perception and action, especially decision-making. Dr. Dietrich's research centers on providing a solid foundation for understanding human choice behavior, the neural implementation of decision mechanisms, and problems of decision-making in neurological and psychiatric disorders, Please welcome Dr. John Dietrich.
Thank you, Andy. Good afternoon. I am John Dietrich, and I would like to introduce you to the topic of cognitive neuroengineering. Deep brain stimulators have been established as a successful treatment alternative for motor disorders like Parkinson's disease when pharmacological options fail. Implanted stimulation electrodes driven by an electrical pacemaker are used to alter the neural circuit that's affected by the disease. New applications of this technology are currently being developed for mood disorders and epilepsy. What if we were able to treat cognitive deficits resulting from neurological and psychiatric diseases such as addiction, attention deficits, or memory loss with implantable stimulators? Cognitive deficits are currently treated pharmacologically. However, these approaches are often too unspecific, have too many side effects, or are not effective at all. Implantable stimulators would provide a new treatment alternative. What would it take to be successful, and why is UC Davis an ideal place for such an endeavor? A fundamental understanding of how our brain solves cognitive problems is key. Here at UC Davis, experimental and computational neuroscientists study learning and memory, attention, and decision-making using a variety of experimental techniques in both humans and animal models. Cognitive neuroengineering relies on these foundations. Another requirement is technology for directly interfacing with the brain. UC Davis researchers develop cutting-edge electrical and optical techniques for measuring and modifying neural activity. Dr. Shakir will tell you more about this in the next presentation. Let's take a step back and consider for now an autopilot for steering a vehicle or an aircraft. Such an engineered device requires a mathematical description of the system or how the system behaves to be able to control it. Similarly, controlling a brain requires a dynamical model of the cognitive system, a set of rules that describe how the large number of neurons in the network interact with each other and how neural activity evolves over time. In addition, we also need suitable control algorithms. This diagram illustrates a currently ongoing project between Professor Kong's lab in engineering and my neuroscience lab. Neural activity from chronically implanted electrode arrays is used to learn a dynamical model for decoding the current state of the brain. The model is also used to determine what stimulation pattern has to be applied to drive the system out of an unhealthy state into a desired state that is closer to how the system normally operates. Another key factor is the ability to test new technology in animal models, a variety of which are being used by researchers at UC Davis. The California National Primate Research Center provides access to non-human primates, which play a critical role in preparing new technology for use in humans. To be able to benefit patients, we closely collaborate with faculty in the departments of neurology and neurological surgery at the UC Davis Medical Center in Sacramento, one of the top 10 hospitals in California. And last but not least, ethical considerations have to be a critical component from the very beginning. Studies of what patients would want from such technology, what kind of alternation of their brain activity they would find acceptable, and what the boundaries are that should not be crossed are crucial for societal acceptance of such devices. Considering also that this technology could not only be used to repair cognitive deficits, but also to augment the cognitive abilities of healthy subjects, the Center for Neuroengineering and Medicine includes bioethicists as key members of research teams in cognitive neuroengineering to be able to deliver exciting new technology responsibly.
Thank you, Dr. Dietrich. Now I'd like to introduce our final speaker, Dr. Erkin Shakir, Associate Professor of Electrical and Computer Engineering. Dr. Shakir's research group uses her expertise the intersection of nanoporous metal synthesis, microfluidics, and device engineering to develop biosensors of various uses. These include pathogen detection, miniature drug delivery platforms, multifunctional neural interfaces, and microphysiological systems to study inflammation, neurodegeneration, and the gut-brain axis. Please welcome Dr. Erkin Shakir.
Thank you, Andy. Good afternoon. I'm Erkin Shakir, an associate professor in the Department of Electrical and Computer Engineering. My colleagues describe several current and emerging uses of neurotechnology and computational tools. I will now focus on our collective efforts and resources to develop such tools. Creating these technologies requires knowledge from many different disciplines, spanning microfabrication, the technology used for making computer chips, neuroscience, biology, computer science, and electrical engineering. This makes neuroengineering a truly exciting interdisciplinary endeavor. Neurons and their interactions with other cells in the body lay at the foundation of many complex neurological processes. These processes are mediated through electrical and chemical means at very different timescales and across an intricate anatomical layout. Malfunctions of these processes manifest themselves as neurological disorders and psychiatric conditions. What if we could monitor the activity and connectivity of neurons throughout the body and modulate them? That is, make changes when necessary. This would provide a picture of the complex neural behavior and allow us to predict the onset of epileptic seizures and intervene so they don't turn into full-blown epileptic attacks. It would also provide insights into cognitive processes like decision-making, so we may learn how to treat disorders like addiction. However, this is not a trivial task and requires rigorous research and engineering innovations. Let's go back to the example of epilepsy that I mentioned a minute ago. While pharmaceutical treatment is an option for managing epileptic seizures, 30 to 40% of patients do not respond to it. In such cases, the epileptic region may need to be surgically removed, resulting in other complications. Another option is to use implantable devices that can detect abnormal electrical activity and intervene to prevent the seizure. In such a system, a neural interface that is thinner than a strand of human hair would be implanted in the brain to continuously monitor electrical and biochemical activity that may indicate an oncoming seizure. The same neural interface would intervene to alleviate the potential seizure by delivering electrical pulses or pharmaceuticals that do not work well when systemically administered. In addition, these implantable devices need to mimic the surrounding tissue by presenting biochemical cues and surface textures, as well as conform to the soft neural tissue by having similar mechanical properties. This is for minimizing the dreaded adverse tissue response that damages both the surrounding tissue and the device itself. Finally, a full implantable device must be able to connect wirelessly with the electronics outside the body for power and information transfer. At UC Davis, we have the complementary set of skills and resources to address the multifaceted challenges in engineering such tools. Numerous research groups focus on different aspects, including the computational approaches such as machine learning. For example, to engineer multifunctional electrodes, our group combines microfabrication and nanotechnology to create porous electrode coatings. These coatings enhance the fidelity of recording electrical signals from neurons and can deliver pharmaceuticals to modulate neural activity. In a complementary approach, my colleagues Professor Weijian Yang and Lin Tian engineer novel optical and molecular technologies to do the same with precise 3D localization in the brain. In these devices, it is critical to pair monitoring and modulating functions to achieve closed-loop control of neural activity. This ensures precise regulation of when and how much medication should be delivered to achieve safe and effective management of a neurological disorder. As described previously, Professor John Dietrich and Professor Zhaodan Kang are developing mathematical models of neural network activity and computational approaches to attain this level of control. The nervous system, particularly via its peripheral branches, also plays a pivotal role in regulating metabolism, inflammation, and even diseases like cancer. Professor Jian Diwan, myself, and other collaborators are developing novel models, such as microfluidic tissue chips that mimic the interactions between the nervous system and the digestive tract, as well as neurodegenerative disorders such as Alzheimer's. Finally, UC Davis offers resources and capabilities to evaluate these engineered systems in a wide spectrum of testbeds, ranging all the way from cell culture models to clinical trials. In addition, several facilities, including the state-of-the-art microfabrication laboratory, enable researchers to create these miniaturized devices. I would like to conclude by emphasizing the pressing need to train the next generation of engineers, scientists, and clinicians while engaging the public and policymakers in the highly interdisciplinary field of neuroengineering. To address this need, UC Davis faculty from many different disciplines are actively contributing to education and outreach. These include cross-training of students in collaborative projects, a vibrant neurotechnology student club, seminar series, and new courses that provide both broad and specialized knowledge on neuroengineering. The collaborative efforts we described today illustrate the synergy among the UC Davis faculty and the rich neuroengineering research and training environment at UC Davis. Thank you.
Thank you, Dr. Shakir. And thank you to all our panelists this afternoon for sharing their innovations in neuroengineering and medicine. Before we dive into the questions, I'd just like to make a comment. It's because of doctors and researchers like our speakers that UC Davis is known for bold ideas, daring approaches, and innovative solutions. And with that, let's move on to the Q&A. We had a number of questions submitted in advance, so we'll dive into those first, and then move on to questions posed during the event via the Q&A box. So I'm going to start off with a question to Dr. Patton. What is a solid source of information on developments to improve quality of life when mobility is impaired?
So thanks, Andy, and thank you for the question. I think that sources of information, I would point the viewer to support groups or foundations that focus on specific disease processes. So, for example, the Dana and Christopher Reeve Foundation looks at people who have had spinal cord injury and provides, if you go to their website, they have lots of resources to help address problems of mobility and how to be in the know about what's happening and in current research and how to source latest technologies. Another example would be the Michael J. Fox Foundation for people who are affected with Parkinson's disease. I'd also point you at the National Institutes of Health, NIH, to the National Center for Medical Rehabilitation Research. So that's National Institutes of Health, NCMRR. And they have a very comprehensive website, and there's a great deal of research that's being supported and a great number of resources that are sourced through that webpage. And finally, another federal agency, which is called NIDLR. It's the National Institute for Independent Living and Rehabilitation Research. That's quite a mouthful, NIDILRR. Independent Living and Rehab will probably get you there in a tag. And they are especially focused, their research focus is especially on reintegrating people into their communities and into work, into school, and into normal life. And so they have a lot of resources there as well.
Thank you. Next question is directed to Dr. Scofield. Can you please define what it means to augment human capacity?
Thanks, Andy. And yeah, that's a really cool question, and it's actually a question that you see coming up quite a lot in popular media, as well as it's this very rapidly accelerating research area. And so I think when we talk about augmenting human capacity, we're really talking about extending what we can do with the conventional human mind and body. And very, very traditionally, we often think about applications in things such as nerve interfaced prosthetics or perhaps exoskeletons that can allow us to lift heavier objects or move more effectively in perhaps military applications, or even neural implants that can allow people that perhaps couldn't hear to begin to hear tones and sounds. And so there's a number of ways in which we can see technology becoming interfaced with individuals in a way that can sort of improve and benefit the quality of life. And just one other thing I thought that was worth mentioning is this doesn't necessarily have to be invasive medical technologies. This can be things, in the areas of virtual reality, where you can use them to do things like treating eating disorders or helping with PTSD for wounded warriors, or even allow people to experience worlds and social circles and environments that wouldn't normally be accessible or even on this earth, but you can do this in virtual reality environments. So I think there's a great area of expertise and a great amount of knowledge here at UC Davis for us to begin to pursue and really sort of push what we mean by extending human capacity. And just to kind of summarize, I think it really means about improving health, improving entertainment and social aspects, as well as potentially, and hopefully improving the quality of life of individuals by working and pairing with technology. Thanks.
Thank you for your answer. Question for Dr. Dietrich. How much of your work uses software-based simulations? What do you see as limits for using simulations to advance your research?
A good question. Yeah, thank you for that. Certainly, software-based or computer-based simulations and also computational models more generally play a critical role in this research. So, for example, when you develop a new algorithm, you would want to test that first on carefully crafted computer-simulated artificial data before applying them to real data. Similarly, when we have or want to test certain ideas about how the brain or how we think the brain is actually able to solve particular cognitive functions, we develop computer models for testing those. However, it's really important to realize that these computer simulations cannot replace our experiments. So that would actually require that we already have a perfect understanding of how the brain is wired and how it operates, which is clearly not the case at this point. So these simulations rather inform new experiments and propel the research forward. So thank you.
Thank you. So you're saying that the simulations inform the experiments and the experiments inform the simulations?
That's exactly right. So you basically have a closed loop, an alternation between modeling and experiments, yes.
Thank you. Question for Dr. Shakir. What are some ethical issues you're making with the changes you're making to human neurology? I mean, we talk about implanting things in people's brains, possibly altering kind of mood or behavior. What are the ethical issues around that?
Mm-hmm. Yeah, this is a great question. Thanks for bringing this up. Like any other technologies, the emerging technologies such as neurotechnology lead to many different ethical considerations, and there are different examples of them at different levels. To give a few examples, one might be, how do these technologies favorably or unfavorably affect human thought, emotion, personal identity? This raises a lot of ethical questions. Another one is, can there be an ethical distinction between how these technologies are meant to repair or restore human capability, or are they also meant to augment human capabilities? And finally, that follows up related to this is, how do we assure the equitable risks and benefits of these technologies? Who takes these risks and who takes the benefits from them? And these are all emerging questions, novel questions that we work with our colleagues that specialize in bioethics to consider them. And we also want to ensure to discuss these in our neuroengineering training programs, so that students and trainees and postdocs are well equipped and are considering these questions as they develop technologies. Thanks for that question.
Thank you. So let's see, another question that came in during the session. Let's see. What are the experimental procedures for testing devices for neuromodulation for epilepsy? And I think this has a couple of different aspects. So perhaps, Dr. Dietrich, perhaps you could address some of the human and animal studies, and then let's see, perhaps Dr. Shakir, you can address on the cellular molecular level. So studying epilepsy.
Yes, so I certainly can say something about that. So also thank you for that question. So a critical component of medical research are always animal experiments, right? So basically, once you have made sure that you have new technology ready to be tested, they would first be used in animal models of epilepsy. There's a variety of them. So for example, there are pharmacological ways to actually create a seizure, and then you can implant the animals with these new devices and test to what extent they are actually able to suppress those seizures. And once you've made sure that these are effective techniques and that they are safe, then you would actually go into a clinical trial and try to use those in patients with epilepsy that are otherwise or cannot be treated pharmacologically.
And
thank you.
Yeah, I would like to take it even one step before. Even before going to the animal studies and human studies, there's a need to do also due to ethical issues of minimizing the number of animals used and human studies. We work with high throughput cell studies, or as I gave an example in the presentation, tissue chip models where you can have mimics of an epileptic seizure on a dish. And we can use these devices or other techniques such as drug delivery to see whether we can prevent the seizures or manage them. And then these can be taken to small animal models, large animals, and eventually to human studies.
So this is an example of how the molecular, cellular, animal, human studies all kind of work together in the course of research, right? Okay, picking up a couple of other questions. And maybe this is a question, a kind of group question, maybe a few people might throw in for this. What do you see as the biggest benefit to society in the next 5 years? And instead of that, what are the biggest challenges to meeting this vision? So maybe, let's see, maybe Dr. Scofield would like to address that first.
Yeah, certainly. I think that, just to partially answer the question, I think in the next 5 years, what we're going to continue to see is the acceleration of many technologies that are going to allow us to answer more questions and understand at a much deeper level the human nervous system, some of the challenges that we'll be facing when it comes to neurological impairment, et cetera. And then we'll also be able to investigate, from my perspective, assistive robotic devices are going to continue to be, made smaller and compact, and battery life is going to continue to improve. And what that ultimately means is that the traditional engineering barriers to using many of these devices are going to start to come down a little bit more and more and more. And so over the next 5 years, I would think that we would be able to see a greater integration and fewer technological barriers that allow us to more closely pair some of these assistive technologies with humans. I'm going to stop there and only partially answer the question because I know the rest of my colleagues on this panel have probably some great insights into the other aspects.
Yes, I was thinking, Dr. Patton, maybe you could talk about what you see ahead for your stroke patients in the next 5 years.
Thanks, Andy. I think, of course, none of us can really predict the future, but looking in my crystal ball, I think I see better knowledge, better science, better informed clinical practice, and that can be really accelerating the pace of what we're doing and what we're providing for patients. That's certainly happening on the neuro rehab side. I think some of these other technologies, the implanted devices that Jochen and Erkin are working with, are very, very exciting. I think we need to be realistic about a 5-year timeline. We may not have them in patients. They may not be ready for the market at that level. That doesn't mean we shouldn't be doing it, and we shouldn't be asking the questions and pushing the boundaries.
Thank you.
I could add something else to that as well. It's also, I think, thinking about it is in a really global research enterprise. I think the tools that are developed here and the scientific information that is created also accelerate the generation and development of these technologies in the entire world. So I think it's a really large collaborative effort, and UC Davis is providing pieces to that as well.
Thank you. Dr. Dietrich, did you have anything you wanted to add?
Well, Carolyn has already mentioned the implantable devices, right? So I would say certainly within the next 5 years, I think we will see that technology come online more for, as I mentioned before, mood disorders, for example, or epilepsy. I would say in terms of cognitive deficits, that would certainly be further down the road to have that treatment option potentially available.
Thank you. Another question here about this. I think in the Chancellor's remarks, he commented on the need to educate and train more scientists and engineers in this area. So perhaps some of the panel could address, maybe Dr. Shakir would like to address this, as you mentioned in your presentation. What should new students heading to colleges think about studying if they're interested in neuroengineering?
Yeah, that's a great question. And I think that's probably one of the also important benefits to the society, as I mentioned, training the next generation of neuroengineers. So there are many different entry points to studying neuroengineering, depending on students' long-term interests. I think at the undergrad level, many different engineering disciplines like electrical, mechanical, biomedical could be a good entry point, supplementing it with technical electives in neuroengineering and data science and statistics, perhaps, and also getting involved in the neuroengineering clubs that are beginning to pop up in different universities. At the grad level, it's more the research part would really shape the students' training. Here at UC Davis, we are working on specialized programs that can that focus on neuroengineering, such as designated emphasis in neuroengineering, that PhD students from different disciplines can benefit and have the community of neuroengineering. So it's also a great way to reach out to mentors and scientists in this field to hear their own stories about how they embarked on this neuroengineering journey.
Thank you. Someone's just shared in the chat, if you're interested in the center, you can go online to neuroengineering.ucdavis.edu to look up more information about the center. Let's see. I have a question here about ADHD and depression. Are there any, this view, I'd be interested to hear about any work being done related to ADHD and depression in terms of neural feedback or enhancement. Perhaps Dr. Dietrich, you'd like to address that?
Yes, so there is certainly work done in the area of depression. So there are already some tests underway to use implantable stimulators to treat those if they cannot be treated pharmacologically. In terms of ADHD, I'm not aware of anything in terms of implantable devices, but there are probably other studies or attempts underway. I don't know whether any of my colleagues have more insights there.
Let's just move on to another question that relates to implants, and maybe this is a question for Dr. Scofield as it relates to interfaces. In regards to the hair size device discussed during the presentation, how is the genetic makeup of an individual assessed, and does that affect how well the device works? Do these kind of implanted devices have to be customized to a particular individual?
Well, I'm thinking here that maybe this hair size device, I'm not sure if that was my presentation. I think I'm going to punt this over to Erkin there. Thank you.
Yeah, I can take that. I think that's a really good question, and it's basically the precision medicine, right? That is also an emerging field. I don't think we are at the level of looking at the genetic makeup for the implant type. I think it is more doing general studies of how these implants affect the tissue response and approaching it from that point of view. But I could see in the future, as these devices more refined, the genetic the background baseline may be taken into account as well. That's an interesting question.
There's a kind of related question about what types of issues are found with brain implants, and what size are they?
I can mention that the electrodes that are inserted into the brain, the cortical implants, typically can be a few millimeters in length, and then maybe tens of hundreds of microns in diameter and width. So they're quite small, but that still leads to some damage that the tissue, that you can kind of think of maybe getting a splint in your finger and the tissue wraps around it to protect the body from it. Imagine a similar thing happens in the brain, and that prevents the electrical signals from being picked up by the electrodes. So that's one of the issues related to some of these recording electrodes, at least.
Is there some possibility that the implant could become rejected at some point?
Yeah, I think some colleagues that actually do recordings with this could probably comment on it as well. But eventually you begin to not be able to record from the neurons, because that's maybe the rejection, that you begin to have that scar covering the electrode, or the electrode begins to fail due to other reasons. Yeah, maybe other colleagues could have some comments on it.
Probably add some information to the size question. So the stimulators that are currently being used for deep brain stimulation are actually not implanted into the head, but they're implanted into body cavity and have roughly the size of a heart pacemaker, right? And then they are just connected up to those stimulation electrodes inside the brain. I think over time we will probably see these devices get smaller and smaller, which is just a general trend that we see with all kind of modern computer technology and electronics.
Thank you. A pre-submitted question that gets to a more general point, and maybe Dr. Patton, this might be a question for you, is can spinal column nerves regenerate when damaged?
Yeah, thanks, Andy. That's a great question. There is emerging evidence in preclinical models. And when we say preclinical, we generally mean animal models. But there's now emerging evidence, certainly in models in rat and models in non-human primate, of regeneration, at least of the cells in the spinal cord. It remains a question whether the connections that are made are functional and whether they lead to a behavioral correlate. But it's very exciting to have evidence that they're actually able to regenerate under certain conditions.
That is exciting. So I had a question perhaps for Dr. Scofield, and maybe this touches on the precision medicine personalizing equipment, but when people are learning to use a prosthetic, are there psychological, mental things that come into play there when they're learning, as much as kind of the physical and sort of neurological interaction?
Yeah, and I think there's many complex factors beyond just psychological and neurological that need to be considered, and that's what makes this a very challenging area to work in. And so it's not as simple as we have a robotic arm or we have an intuitive way to control it. It's very much a learning process. There's an individual who is now recovering after a very major surgery and a very major injury. And there's so many complex factors that ultimately add up to the effectiveness of a prosthetic prescription and the effectiveness of their ability to use that device to, restore some of the function that has been lost with an intact limb. So the answer is yes, Andy, and it's yes and so much more. So it is a very complicated way, and it's something that, as an engineer, we cannot solve without speaking with clinicians, without working with physical therapists, and without working with neuroscientists. So that's one of the really exciting things about being here and why I'm very excited to be here at UC Davis.
Just picking up on that point, the whole center is an example of how people in diverse fields work together and produce uniquely innovative solutions. And there's a question related to that. How is the expertise at UC Davis unique in allowing the blurring of human and machine actions?
Yeah,
maybe.
Sorry,
go John, as you're still online.
I'm still online and I'm still just primed to answer. So I apologize for stepping on your toes. I think that, tapping into that idea of very interdisciplinary, a number of centers and a number of very experienced individuals in complementary areas is a very important aspect to that. But it's also the applications and the ability to broaden what we're learning in specific fields. So if we look at robotic prostheses, we talked briefly at the end of my presentation about how we have just a variety of applications that can really pull from this information gained. And that's anything from, robotic prosthetic limbs through exoskeleton systems, all the way up to we have an astronaut working in our center here that, we're working with him to perform work in spacecraft robotics. And a lot of the same fundamental principles that apply in prosthetic limbs can apply in many, many areas. And so that's an answer, and I'm going to be quiet now and allow the mic to get passed on to someone else.
Carolyn or Erkin, would you like to add to that? Perhaps Carolyn as a co-director of the center.
I think John handled it very nicely. Plus, he's very eloquent. I think we've hit that.
So this is a little bit of a technical question. Is there any work being done to use induction rather than electrical or chemical stimulation?
Yeah, I was just about to type an answer to that, but I can also answer it live here. So yes, you can certainly use magnetic fields to stimulate the brain. In fact, transcranial magnetic stimulation, a non-invasive technique, has been used for quite a while, and it's being used for both research as well as therapeutic purposes. And I think Carolyn can probably add something to that since she's using the technique herself.
It's a method, and it's all a matter of what one wants to do with it. But some of the data that I showed in my presentation were generated with transcranial magnetic stimulation. And so what's very nice about it is considered non-invasive, and to the human experiencing it is quite unperturbing, and it's very safe. It's very safe to use. So in terms of for us as scientists or even as clinicians, it's a wonderful technique because it offers us a lot of options to be probing the nervous system.
Thank you. I think this will have to be our last question. Very exciting presentation. Just wondering if the center will address business issues. I can see many patents emerging, possible startups, so these technologies can move to the clinic. And Dr. Patton, do you want to address that?
Yeah, thank you. And the answer is yes. That absolutely is part of our vision and part of what I was trying to get at in talking about the valley of death and the ups and downs with this. We definitely want to work with industry partners. We want to work with developers. We certainly are. The attendee is very insightful that yes, there's a lot of intellectual property that can emerge from here, and that's one of the exciting things about this multidisciplinary field. We also have the opportunity with development of Aggie Square, which is intended to be a startup environment between the medical school and between our campuses that is really there for catalyzing activity within industry partners. And we think we're very well positioned to participate in that. And so we're excited that people are paying attention and asking these questions.
Thank you. And thank you all for your thoughtful questions. I think that's all we have time for right now. You should now, or in a moment, see a poll appear on your screen. Please take a minute to answer. There it is. I'd like to thank all our panelists for sharing their time and insights this afternoon on how they're developing neuroengineering tools and methods to better understand the brain and treat neurological disorders. And I'd also like to thank you all today for joining us and for your philanthropic support. As the Chancellor highlighted in his video, UC Davis is one of the few universities with world-renowned programs in neuroscience, engineering, human and veterinary medicine at the forefront of innovation and discovery. It's strengths like this that allow us to lead the charge in helping us learn how to solve tomorrow's challenges today. Whatever your passion may be, there is a way you can help support it. If you're interested in giving to any of the initiatives discussed today by our panelists, you can contact Gabriella Lee, Associate Director at the Center for Neuroengineering and Medicine. We hope you're all staying healthy and safe, and we look forward to connecting with you again soon. Good afternoon and goodbye.